Welcome back to Operating Systems Crashcast. I'm Victor, and today we're wrapping up Chapter 5 on process synchronization with a comprehensive summary. Sheila, are you ready to dive in?
Absolutely, Victor. This chapter has been a rollercoaster ride through the intricacies of process synchronization. Let's start by reminding our listeners about the critical section problem that's been at the heart of our discussions.
Great idea, Sheila. The critical section problem is all about ensuring that when one process is executing in its critical section, a part of the code where it accesses shared resources, no other process is allowed to do the same. It's like making sure only one person uses the bathroom at a time in a shared apartment.
Exactly, Victor. And to solve this problem, we need to satisfy three key requirements: mutual exclusion, progress, and bounded waiting. Mutual exclusion ensures that only one process can be in its critical section at a time. Progress means that processes outside the critical section can't prevent others from entering it. And bounded waiting limits how long a process must wait to enter its critical section.
Well put, Sheila. We've explored various synchronization methods to tackle this problem. Let's start with the hardware support. We discussed atomic instructions like test and set and compare and swap. These are special operations that can't be interrupted, allowing us to implement more complex synchronization tools.
That's right, Victor. Building on these hardware primitives, we then looked at higher-level synchronization tools. Mutex locks, for instance, provide a simple way to protect critical sections. But the real workhorses we covered were semaphores and monitors.
Absolutely. Semaphores are particularly versatile. They can be used for both mutual exclusion and process coordination. Monitors, on the other hand, provide a more structured approach, encapsulating both the shared data and the operations on that data.
Don't forget about the classic synchronization problems we discussed, Victor. The bounded buffer problem, the readers-writers problem, and the dining philosophers problem. These aren't just academic exercises. They represent real challenges in concurrent programming.
You're absolutely right, Sheila. These problems help illustrate the complexities of synchronization in practical scenarios. The bounded buffer problem, for instance, is analogous to managing a shared queue in a producer-consumer system. The readers-writers problem mirrors situations where data can be read simultaneously, but must be written exclusively.
And the dining philosophers problem is a great way to understand deadlock and starvation issues. It's fascinating how these abstract problems relate so closely to real-world synchronization challenges in operating systems and concurrent applications.
Indeed, Sheila. We also touched on some alternative approaches to synchronization. Transactional memory, for instance, offers a way to simplify concurrent programming by allowing a group of load and store instructions to be executed atomically.
That's a great point, Victor. And let's not forget about OpenMP and functional programming languages. These approaches aim to make concurrent programming more accessible and less error-prone. It's important for our listeners to understand that synchronization is an evolving field with ongoing research and development.
Absolutely, Sheila. As we wrap up this chapter, what do you think are the key takeaways for our listeners, especially for those preparing for interviews or practical applications?
Great question, Victor. I'd say the most crucial points are understanding the critical section problem and its requirements, knowing the basic synchronization tools like semaphores and monitors, and being aware of the classic synchronization problems. It's also important to understand the trade-offs between different synchronization methods in terms of complexity, performance, and ease of use.
Excellent summary, Sheila. I'd add that it's vital to recognize the potential pitfalls in concurrent programming, such as race conditions, deadlocks, and priority inversion. Being able to identify and mitigate these issues is a valuable skill in both interviews and real-world scenarios.
Absolutely, Victor. And let's not forget the importance of choosing the right synchronization primitive for the task at hand. Sometimes a simple mutex is sufficient, while other situations might call for more complex solutions like monitors or even alternative approaches like transactional memory.
Great point, Sheila. As we conclude this episode and Chapter 5, I want to remind our listeners that process synchronization is a fundamental concept in operating systems and concurrent programming. The principles we've discussed here apply not just to traditional operating systems, but also to distributed systems, cloud computing, and even multi-core programming on your smartphones.
Absolutely, Victor. The challenges of synchronization are more relevant than ever in our increasingly parallel and distributed computing world. Understanding these concepts is crucial for anyone working in software development, systems administration, or any field involving concurrent systems.
Well said, Sheila. And with that, we wrap up our discussion on process synchronization. Thank you all for listening to Operating Systems Crashcast. In our next episode, we'll be diving into Chapter 6 on CPU scheduling, so stay tuned.
Thanks, everyone. We hope you found this summary helpful. Keep those processes synchronized, and we'll see you next time.